My name is Manish Kumar and my enrollment number is E19Cse102. I'm a third year BTech student of Computer Science of Bennett University, and today I will be doing seminar on quantum computers. So let's begin.
So now we will start with our seminar which is based on quantum computers. First we will start with introduction. For the majority of our existence, human technology was limited to brains, fire and sharp sticks. While fire and sharp sticks evolved into power plants and nuclear weapons, the most significant advancement has occurred in our minds. Since the 1960s, the power of our brain machines has grown tremendously, allowing computers to get smaller while also becoming more powerful. However, this process is approaching its physical limit. Computer components are getting close to the size of an atom. To understand why this is an issue, we must first establish certain fundamentals. Now we will start with basics. A computer is made up of extremely basic components that perform very basic tasks: data representation, processing methods, and control mechanisms. Computer chips are made up of modules that include logic gates and transistors. Transistor. A transistor is the most basic type of data processor used in computers. It is essentially a switch that can either block or allow information to pass through. The data is made up of bits that may either be changed to 0 or 1. To represent more complicated information, several bits are combined. Logic gates are made up of transistors that perform extremely basic tasks. An AND gate, for example, sends a 1 output if all of its inputs are 1 and 0 output otherwise. Finally, logic gates are combined to construct useful modules, such as adding two integers. We can multiply once we can add, and once we can multiply, we can do anything. Because all the fundamental operations are either easier than first grade maths, we may consider a computer as a collection of 7-year-olds completing simple mathematical problems. They could compute everything from astrophysics to Zelda if there were enough of them. Quantum physics, on the other hand, is complicating matters as components grow smaller and smaller. A transistor is just an electric switch. Electrons are charged particles that move from one location to another. As a result, a switch is a channel that may prevent electrons from traveling in one way. Now we will talk about shrinking transistors. Today, transistors have a size of 14 nanometers, which is roughly 8 times smaller than the diameter of HIV virus and 500 times smaller than of red blood cell. In quantum world, physics operate in a very different way than we are used to, and regular computers just cease working. We are nearing a physical impediment to our technological advancement. To tackle this difficulty, scientists are developing quantum computers that can take advantage of this peculiar quantum feature. Bits are the smallest unit of information in conventional computers. Qubits, which may be adjusted to one of the two values, are used in quantum computers. So, now, what is a quantum computer? A quantum computer is a machine that performs calculations based on laws of quantum mechanics, which is the basic behavior of particles at subatomic levels. A quantum is a smallest possible discrete unit of any physical property in quantum computing. Computation depends on the principle of the quantum theory. Now, what is quantum computing? Quantum computing is the area of study focused on developing computer technology based on the principles of quantum theory, which explains the nature and behavior of energy and matter on atomic and subatomic levels. Computers based on this theory are smaller and faster than the digital computers. Calculations based on the laws of quantum mechanics uses mechanical phenomena to perform operations on data. Operations are done at atomic and subatomic levels. Now we will talk about qubits. A qubit can be a single photon or any two-level quantum system such as spin and magnetic field. The conceivable state of the system, like horizontal or vertical polarization of photons, are 0 and 1. The qubits in quantum world doesn't have to be just one of those. It may be in various proportion of both states at the same time. This is referred to as superposition. When we verify its value, for example, by passing a photon through a filter, it may choose whether to be vertically or horizontally polarized. So long as qubit remains unseen, it is in superposition of probabilities 4, 0 and 1, and we cannot tell which one it will be. However, it collapses into one of the definite state the moment we measure it. The ability to superimpose is a game changer. At any one time, 4 classical bits can be in one of the 2 to the power 4 possible configurations. There are a total of 16 potential combinations, but we can utilize only one of them. 4 qubits in superposition, on the other hand, can be in all 16 configurations at the same time. With each additional qubit, this number climbs exponentially. 20 of them are already capable of simultaneously storing a million values. Entanglement, a tight link that causes each qubit to react instantly to the change in the state of other, no matter how far they are, is a truly strange and unintuitive quality qubits may have. This means that by measuring only one entangled qubit, the characteristics of its companion may be deduced without having to look. Qubit manipulation is also a brain teaser. A basic set of inputs is fed into logic gates, which creates a single definitive output. A quantum gate manipulates superposition as input, rotate probabilities, and output another superposition. So a quantum computer entangles and manipulates probabilities by quantum gates, then measures the result, collapsing superpositions to a real sequence of zeros and ones. This implies that we may perform all the operations of computation that are feasible with the configuration at the same time. In the end, we can only measure one of the outcomes, and it will almost certainly be the one that we want. However, by skillfully utilizing superposition and entanglement, this may be considerably more efficient than on a traditional computer. While quantum computers are unlikely to replace our home computers, they are far superior in several areas. Now, quantum properties used in quantum computers are decoherence, entanglement, and uncertainty principle. Decoherence is one of the biggest problems in quantum computers. It states that if a coherent or a superimposed state interacts with the environment, it falls into a classical state without superimposition. So, for a quantum computer to work with superimposed states or coherent states, it has to be completely isolated from the rest of the universe, not observing the state and also not measuring it. The second one is entanglement, most important property in quantum computers. It states that two or more particles can be linked, and if linked can change property of particle, changing the linked one. Two particles can be linked and changed each other without the interaction. The third one is the uncertainty principle, which is uncertainty in position product with uncertainty of momentum is greater than or equal to Planck's constant by 4 pi. Quantum systems are so small it is impossible to measure all the properties of quantum system without disturbing it. As a result, there is no way of accurately predicting all the properties of particle in a quantum system. Now, advantages of quantum computer. Quantum computers have ability to solve scientific and commercial problems, process data in much faster speed, capabilities of conveying more accurate answers. They can compute more in less time. They can be used to secure web pages, encrypt emails, could process massive amount of data. One of the major advantages is database searching. A regular computer might have to evaluate every single entity in database to locate something. Quantum computer algorithms only require a square root of that time, which is considerable difference for large datasets. The most well-known use of quantum computer is destroying IT security. A quantum computer with exponential speed, on the other hand, might do it in a flash. Applications of quantum computers include encryption technology, ultra-secure and super-dense communication, improved error and correction and error detection, cryptography, searching, factorization, encryption problem and quantum computing problem, molecular simulations and simulating. Simulating are another intriguing new use. Quantum simulations are resource intensive, and even for a larger object like molecules, they frequently lack precision. Quantum simulations might provide new information about proteins, and revolutionize medicine. In conclusion, I would like to say a quantum computer has theoretical capability of simulating any finite physical system that may hold the key of creating an artificially intelligent system. The quantum computer power to perform calculations across a multitude of parallel universes gives it ability to quickly perform tasks that classical computers will never be able to do practically. Right now, we do not know if quantum computers will just be a specialized tool or a big revolution for humanity. We have no idea where the limits of these technologies are. Thank you very much for your patient listening.